Let's wait for 5 minutes before we start the session. Okay. So today we will be solving the assignment problems of week 3. which are based on point set topology. So, in order to start with those problems, let's first recall the basic definitions that one must be aware of. So, yeah, let's start with firstly limit point. Let's start with the some definitions. Firstly, we have limit point of a set. Limit point of a set. Now, suppose A be a subset of R. A real number P belonging to R is said to be a limit point of A. This P need not necessarily be in the set A. This is again a real number. A is a subset of real numbers. P is a real number, and we say that P is a limit point of A if this in open interval P minus R to P plus R intersection with the set A minus P, this is non-empty for every R positive. So basically, if we look at the real line, if this is a real line and this is somewhere point P, no matter what R I take, P minus R to P plus R, this interval should have some point of A except for P. P need not be point of A, but we should always be able to find at least one point somewhere in P minus R to P plus R except from P that this belongs to A. And this should happen for every R positive. Then we say that this P is a limit point of the set A. Next comes the definition of the interior point. Next we have interior point. A set. Now again, suppose A is a subset of R. A is a subset of R, and we say that some point, suppose let's call it P only. P is an interior point of A if there existed some R, if there exists, see above for limit point, it was happening for every R positive, and in this case we are saying that there exists some R positive such that this interval P minus R to P plus R is completely contained in A. Clearly, one can notice that from here, P must be in A. So, a limit point need not necessarily be an element of the set for whatever it is the limit point. Basically, a limit point of set A need not be in the set A, but the interior point must be a set of must be an element of the set. And in fact, there exists an interval around, or we should say a neighborhood around P, which is contained completely in the set A. So if we look it on the real line, if this is point P, then this interval P minus R to P plus R, this should be completely contained in the set A. Then only we call P as an interior point. Using these interior points and limit points, we can judge whether a set is closed, open or not. For that, yeah, we have our next definition. Definition number 3, which is of open set. A set, and also we denote, let's mark it as, we denote by A prime the set of all limit points of A, and we denote by A naught by the set of all interior points of A. Next comes the definition of open set. Set A in R is called open set if the set of all interior points or is the set itself. That means if A naught is equal to A. That is, every point of the set A is an interior point of A. If such condition happens, then we say that the set A is an open set. And next we have closed set. So for this, one can go for, we have two options. Either one can see whether its complement is open. So firstly, if the set R minus A, the complement of the set A is open, we say that A is closed. Secondly, the main definition in terms of limit point, if a set A subset of R is said to be closed if the set of limit points of A is contained in A. That is, all the limit points, of the set A are contained in A. A contains all its limit point. And the last one is the closure of a set. Closure of a set, we denote it by A bar. We say A bar is equal to A union A prime. This is called the closure of A. I hope these definitions are clear to everyone. If you have any doubt in any of the definition, you can ask. Otherwise, we'll move forward and solve week 3 assignment problems, which are mainly involved around all these definitions. Okay, let's move to next first question. Question number 1. State whether true or false True or false? If A subset of R is open and closed, then A is an interval. Now suppose A is a subset of R, A is closed and A is open. We know that complement of a closed set is open. That means R minus A is open. And hence, complement of open set is closed. That means R minus A is closed. Now if A is a set such that it is open as well as closed, then its complement must also be open and closed. That means if A is such a set, then A complement is also such a set, and we all know that there exist only two such sets in the set of real numbers, the empty set and its complement as well, the set of real numbers. These are the only two sets in the set of real numbers which are open as well as closed simultaneously. Now clearly we can write phi to be the open interval a to a for any a in R, and R can be written as open interval minus infinity to infinity. Then also clearly both of them are intervals, and hence the statement is true. I hope this is fine. So basically, the main idea is the fact that only two sets in the set of real number are such that they are open as well as closed at the same time, and they are the empty set and whole the set of real numbers. Both of them are obviously intervals. Therefore, the given statement is true. Okay, let's move to next question. Question number 2. Again, state whether true or false. Every subset of R every subset of R which is countable and compact must be finite. So in order to solve this problem, basically in order to conclude whether this is true or false, one must be aware of the terms countable set and compact set. So in layman terms, countable set is a set whose elements can be enumerated. So basically if we can write A to be equal to some x1, x2, x3 and so on. Basically, I can enumerate the elements of the set A. We call it countable. A is called countable. And we all know some basic examples of countable sets. Firstly, a finite set, if it has some finite number of elements, a finite set is always countable. We also have infinite countable sets. For example, the set of natural numbers. It has has infinite elements, 1, 2, 3, but we can always enumerate them. Then we have the set of integers, also the set of rationals. These are some basic examples of countable sets. Next comes the compact set. We call a set a subset of R is called compact if it is closed and bounded. If it is closed and bounded. Now we need to, what they are saying, that every subset of R which is countable and compact must be finite. So, is it true? It need not be finite. Yeah, if we are saying that this is false, one must be able to give some example. And a very good example would be some subset of rationals, because we know that rationals can be infinite even in bounded domain. So even if being bounded set, they can have infinite number of elements. So if I consider the set A, which is close 0 to 1, intersection Q. So basically we are collecting all rationals in the closed interval 0 to 1. Obviously we all know that this set is infinite. Then A is an infinite set. Since A is a subset of closed interval 0 to 1, it is bounded. Yeah, we should be able to get an example which is an infinite set and compact. So, secondly, we'll show that this is compact. Compact means closed and bounded. So, clearly it is bounded set. Now, since A is a subset of closed interval 0 to 1, this implies 0 less than equal to A less than equal to 1 for every A in A. That means A is bounded. Next, we will show that this is closed as well. Claim that A is closed. That is, A prime is contained in A. So any limit point of A must be in A. I think I did something wrong. Okay, let's look at this problem at the end. I think I'm doing missing out something. Let's move to next. I'll repeat this at the end. We'll look at this problem again. I, Question number 3. State whether true or false the set Z is a subset of R is closed. We will show that yes, the set is closed. So for that, we will show that its set of limit points is contained in Z. Solution. We claim that Z prime is contained in Z. So basically every limit point of Z is an element in the set of integers Z. Now let P be any point in Z prime. This implies P is an element in R such that P minus R to P plus R intersection Z minus P. This is non-empty for every R positive. Now, since this P is a real number, it can either be an integer or a non-integer. So we'll start with case 1 when this P is an integer. Now, if P is an integer, then we have our real line P minus 1, P plus 1, and this interval P minus 1 by 2 to P plus 1 by 2. Now suppose if P was a limit point, then this intersection must always be non-empty. But this should be non-empty for every R positive. So this should be non-empty for R equals to 1 by 2 as well. Now if P is a limit point of Z, then P minus R, P plus R intersection Z minus P, this should be non-empty for R equals to 1 by 2 as well, because this is happening for every R positive. So this should happen for R equals to 1 by 2 as well. But clearly one can notice that there is no integer in between this interval, because before P it's P minus 1, which is not in this interval. After P, this is P plus 1. So but this P minus 1 by 2, P plus 1 by 2 intersection Z minus P is an empty set. Therefore, P does not belong to Z. Now, since P is a limit point, this should happen. But since this is not happening, therefore this case fails. Therefore, P cannot be an integer. Therefore, now there is only one possibility, that if P is some limit point of the set of integers, then it should be a non-integer. So let's see what happens for the case of does not be P not belonging to Z. Then we have case 2 where P is a non-integer. In this case, now since P is a real number which is not belonging to a set of integers, then clearly we can find some integer, say n, in Z, such that n is strictly less than p, strictly less than n plus 1. Obviously, every real number lies between some integers. So, if we look at the real line, this is n. This is somewhere p, and then we have the next integer n plus 1. Now, since p is limit point, now since p is a limit point of z, then again p minus r, p plus r intersection z minus p is non-empty for every r positive. Now if I take this r to be minimum of n plus 1 minus p, this distance, p minus n, this distance, upon 2. So suppose minimum of n plus 1 minus p and p minus n was n plus 1 minus p. So that means this is the smaller distance and we are taking half of it. So our interval is something like this. So eventually this interval will never contain any integer because p is not an integer. The next integer after p is n plus 1, which is obviously not in this interval because we have taken r in such a way that our interval does not contain any integer. Now this implies p minus r, p plus r intersection z minus p is empty. Now this gives us a contradiction. Hence both the cases fails. What does that mean? Now this means that if p is a limit point, then it is neither an integer nor a real number which is not an integer. So basically it is nothing. That means we do not have any limit point. Hence z does not have any limit point. Now this limit point. Now this means Z prime is an empty set. And we know that empty set is always a subset of any set. That means this is a subset of Z. This implies Z prime is a subset of Z and hence Z is closed. That's what we wanted to show. The set of integers is a closed set. That means the given statement is true. I hope this proof is fine with everyone. If you have any doubt, please ask me. You can go through this proof again and please ask if you have any doubt. Okay, so let me go through this question number 2 again. I realized what I was doing wrong. So yeah, for the example, the counter example for this case was, if we consider A, yeah, this is wrong. Consider the set Consider the set A to be 0, 1, 1 by 2, 1 by 3, and so on. So basically this is 0 union 1 by n belonging to n. Now this set, clearly this is bounded, since 0 less than equal to x less than equal to 1 for every x in A, this implies x is bounded. Clearly, sorry, this implies A is bounded. Clearly, A has infinite elements, and the limit point. Can you tell me what will be the limit point of this set? Ah, there's no one. Okay, so 0 is the only limit point of this set, because we know that the sequence xn equals to 1 by n, the sequence converges to 0. This implies for every r positive, there exists some capital N in n such that mod xn minus 0, this is less than r, for every n greater than equal to n. That means 0 minus r, 0 plus r, intersection A is non-empty. And this happens for every r positive. That means 0 is a limit point of A. In fact, this is the only limit point. One can easily check that for the points 1, 1 by 2, 1 by 3, and so on. We can always find an interval such that this find some r such that 1 by 2 minus r, 1 by 2 plus r, intersection A minus 1 by 2 will be empty. Eventually, rest of the points cannot be limit point, and hence 0 is the only limit point. Only limit point of A, which implies A prime is singleton A 0, which is contained in A, which implies A is closed. Hence, we are able to find a closed and bounded set, which is not a compact. We could find a compact countable set which is not finite, and A is countable. Thus, the given statement is false. I hope this is fine with everyone. Okay, then let's move to next question. Question number 4. State whether true or false there is no subset of R which are neither bounded, which is neither bounded nor, sorry, neither bounded below nor bounded above. So the statement says that there exists no such subset of R which is neither bounded below nor bounded above. So is it true? I would like you to think whether, yeah, if this is false, then we should be able to find some set which is neither bounded below, which is basically which is unbounded below as well as unbounded above. So yeah, obviously this is false. One can get many examples. For example, if we take the set of rationals, if I take A to be set of rationals in R, they are the set is neither bounded below nor bounded above, and clearly this is a subset of R. Neither bounded below nor bounded above. Or we can say that this is A is unbounded below as well as unbounded above. Therefore, the given statement is false. So yeah, let's move to next question. Question number 5. Let A be a subset of R, be non-empty, be non-empty, and P belonging to R be such that P is the only limit point of A. Only limit point of A which is not in A, and P does not belong to A. That means P has a limit point which is outside A. Then we have two options. A is open. Secondly, A is closed. And A is both open and closed. And none of the above. Now, firstly, I think the point of closeness, it must be clear by the definition. We all know that a closed set has all its limit points. So basically, by the definition of closed set, we know that by the, so here, let me start with. Now, since P is the only limit point of A, that means P is, sorry, that means A prime, this is equal to the singleton set P. And since P does not belong to A, that means A prime is not a subset of A, which by the definition of closeness, this implies A is not closed. Why? Because we know that A is closed if and only if A prime is a subset of A. Now this implies that option 2 and option 3 are incorrect. Now, what can we say about the openness of the set? Whether the set will be open or not. Can you say anything? Whether the set will be open or not.
Yes, ma'am, it is open.
How? So open set is the set of is a set such that all of its points are the interior points. So will it be open? Now suppose if A is open, then A naught is equal to A. That means all of its points are its interior points, and A complement, which is R minus A, is closed. Because also we know that the complement of closed set is open, complement of open set is closed. So now if A complement is closed, that would imply that all the limit points of R minus A are contained in R minus A. So can you say anything about the limit points of R minus A? So basically, based on the information given in this problem, we cannot directly say whether this will be open or not. So instead, one can look for some examples of such set. So if we start with this, if we consider the set A to be 1, 1 by 2, 1 by 3, so on. So this is 1 by n. n in n. Clearly, this is a non-empty subset of R and it has only one limit point. What will be that limit point? Clearly, p is equal to 0 is the only limit point of A. So we are in the same scenario. So can you say anything about this set A, whether this is open or not? Obviously, this is not open, because if this is open, then all the points must have been the interior points. And obviously, 1 minus 1 by 3 to 1 plus 1 by 3, this interval is not contained in A. So let me write it properly. Next, we can see that A is equal to 1, 1 by 2, 1 by 3, so on. This is 1 by n belonging to n, has only p equals to 0 as a limit point, with clearly p does not belonging to A. That means the set A satisfies all the conditions of the given problem, and and this A is not open. A is not open because I think there's some lag in my pencil. Because if A is open, then clearly 1 which belongs to A should also be an interior point. Is my screen visible?
Yes, ma'am.
So are you able to see the reasoning that I said? If A is open, then all the points must be the interior points of the set A. But if we look at the point 1 or even 1 by 2, the interval, we can always find an interval around 1 which will not be inside A. Be an interior point. I think it's my notes is not working. Yeah. Now, since if A is open, then 1 belonging to A must be an interior point of A. That means we should be able to find there exists some R positive such that 1 minus R to 1 plus R, this is contained in complete A. But clearly we can see that if this is 1 and this is somewhere 1 by 2, this interval, whatever r we take, this whole interval cannot be in A. But since 1 minus r to 1 plus r is not contained in A for every r positive. R equals to 0, this interval will be in A, but we need r positive. Similarly, we can find many more examples. Therefore, A is not open. So I hope this is clear now how this set will not be open. So therefore, the point first also gets discarded and we are left with just the point 4, none of these. So let's say we get point 1 also incorrect. Therefore, correct point is fourth, none of these. I hope this is fine how the set is neither open nor closed. Okay then, let's move to next question. Question number 6. State whether true or false. Let A be a subset of R, be non-empty, non-empty, bounded above set, bounded above. Now define the set minus A. It has all elements of the form minus A, minus small a, where A belongs to capital A. They are saying that then the set minus A is bounded below, and this infimum of minus A is equal to minus supremum of A. So now since A is a non-empty bounded above set, then obviously it must have an upper bound. Now since capital A is bounded above, that means it has an upper bound. That means there exists some alpha positive, or I should write some u positive, not necessarily u positive, such that A is less than equal to u for every A in A. That means minus A is greater than equal to minus u uh, for every A in A. Now the terms of the type minus A are elements of the set minus A. So if this implies, we can write B is greater than equal to minus u for every B equals to minus A, and this B belongs to the set minus capital A. That means this point minus u is a lower bound. Yeah, here instead of positive, yeah, positive will also be fine. We should write a real number u. This minus u is a lower bound of minus a. That means minus a is bounded below. Now this gives us an idea that the given statement might be true. So yeah, the first point is true. the set minus A is bounded below. Next, let's see whether we have this relation as well or not. So we start with notation. Let's denote alpha to be infimum of minus A and beta to be supremum of. Okay. So now, since alpha is infimum of minus A, now since alpha is infimum of minus A, that means alpha is less than equal to B for every B in minus A. Now, since every element in minus A is of the form minus A, that means alpha is less than equal to minus A for every A in capital A, which implies minus alpha is greater than equal to A for every A in A. Now, this gives us that minus alpha is an upper bound of A, because obviously this is greater than equal to every element in capital A. Now we have a relation between the upper bound and supremum. We know that upper bound is always greater than equal to the supremum. Basically, by the definition of supremum is the least upper bound. That means minus alpha must be greater than equal to supremum of A, and we denote the supremum of A by beta. Therefore, we get minus alpha is greater than equal to beta. Similarly, since beta is equal to the supremum of the set A, that means beta is greater than equal to A for every A in A, which implies minus beta is less than equal to minus A for every A in A. Now the terms of the type minus A are actually the elements of minus capital A. This implies minus beta is less than equal to B for every B equals to minus A belonging to the set minus A. Now, since minus beta is less than equal to every element in minus A, this implies minus beta is a lower bound of minus A. Then again, we have a relation between lower bound and infimum. We all know that infimum is the greatest lower bound. This implies minus beta is less than equal to infimum of minus A. And by notation, this is equal to alpha. This gives us minus beta is less than equal to alpha, or beta, a second, I did something. Yeah, okay. Now this implies alpha is less than equal to minus beta. Yeah. And from here we have minus beta is less than equal to alpha. Hmm. So marking this as number 1 and this one as number 2. By first and second, we get alpha is equal to minus beta. That's what they are saying. Infimum of minus A is equal to minus supremum of A. That means infimum of A is equal to minus supremum of infimum of minus A is equal to minus supremum of. Yeah, I hope this, yeah, proof is fine. Just go through this once again, and if you have any doubt at any point, please let me know. So therefore, the given statement is true. Okay, so let's move to next question. Question number 7th. Let In be the interval given by A and Bn, closed interval A and Bn, be a sequence of closed and bounded intervals in R such that In intersection Im is non-empty for every n not equal to m. Let I be the intersection of all these Ins n and n, then which of the following is true? So basically we need to see whether this I will be non-empty or empty or non-empty or closed or not. For that, the main thing that we need, that one must be aware of, is the fact that intersection of closed sets is always a closed set. So yeah, let's start with that. Claim 1. Suppose A and B are two closed sets, then A intersection B is also C is equal to A plus A intersection B is also closed. Kindly look for this proof. I'll come back in 2 minutes. I would like you to try it first. So basically, you need to use the definition, the fact that a closed set has all its interior points. So basically, if C is closed, then C prime must be a subset of C. Try to prove that. I'll come back in 2 minutes. Yeah, after that, we'll discuss it. Okay, so now we are given that the set A and B are closed. That means since A is closed, this implies A prime is a subset of A. And since, yes,
Because
do you want to say something? Okay,
sorry, ma'am, I unfortunately touched my mic.
okay, fine. So also since B is closed, That means B prime is a subset of B. We'll show that C prime is also a subset of C. So for that, let us start with some arbitrary limit point of C. Now suppose x is a limit point of C. Now let x belongs to C prime. That means x is a limit point of C. X is a limit point of C. That means x minus r to x plus r intersection C minus x. This set is non-empty for every r positive. That means there exists some yr. That means there exists yr belonging to the interval x minus r, x plus r intersection C minus x for every r positive. Now, since C is A intersection B, this implies yr belongs to x minus r, x plus r intersection A intersection B minus x for every r positive. Now, since this belongs to uh, this yr belongs to some intersection of sets, that would imply that yr belongs to x minus r, x plus r intersection A minus x, and yr belongs to x minus r, x plus r intersection B minus x. And this is happening for every r positive. Now this implies that the interval x minus r, x plus r intersection A minus singleton x, this is non-empty for every r positive, and the interval x minus r, x plus r intersection B minus singleton x, this is non-empty for every r positive. Now this tells us that this point x is a limit point of A, and this tells us that x is a limit point of B. That means x belongs to A prime and x belongs to B prime. Now since A and B are closed, so this A prime is a subset of A, B prime is a subset of B. That means x belongs to A and x belongs to B, which implies x belongs to A intersection B, which is equal to C. So we started with an arbitrary point in C prime, and we landed to the point that this x belongs to C, which implies that C prime is a subset of C, and hence C is closed. Now here we had proved that if we have two sets, the intersection of these two if we have two closed sets, then their intersection will be uh, closed. Similarly, you can see that if even if we have arbitrary number of closed sets, their intersection will also be closed. That would be a task for you. Now let's see how this will be helpful for us in order to solve this problem. So we are given some arbitrary closed intervals in such that in intersection im is non-empty, and we consider I to be the intersection in. We will show that this I is actually non-empty closed set. So for that we will construct some new sets fn
Ma'am,
as follows.
I have a doubt.
Yes,
In the question, I have to prove that the intersection between two intervals is non-empty, right, ma'am?
non-empty and closed. Not just interval, these are closed intervals.
Oh, I have to prove that they are closed sets.
Closed sets, yeah. We are given that in are closed intervals, and we will show that closed intervals such that their intersection is always non-empty, then we will show that the overall intersection will also be non-empty, and in fact that intersection will be closed as well. So for that,
Okay.
yeah, for that, we will construct a new set of closed intervals using these. So I consider f1 to be equal to I1. Then I take f2 to be I1 intersection I2. Clearly f1 is closed. Now since f2 is intersection of two closed sets, we know that I1 intersection I2 is non-empty because IN intersection IM is non-empty for every n not equal to m. So this will imply that f2 is non-empty. And in fact, since it is intersection of two closed sets, f2 will be closed. Also, this will be a subset of I1, which is f1. So we have a set closed set f1. Then we have a closed set f2, which is a subset of f1. Then using this, we define f3 to be, so yeah, instead of I1, I should write here f1. I define f3 to be f2 intersection I3. Now since f2 is a closed set, I3 is a closed set, this will also be a closed set. And again, this will be non-empty. f3 is non-empty. f3 is closed. And clearly f3 is a subset of f2, and so on. So eventually how this sequence will look like, suppose now this is our f1, this was a closed interval, f2 is a subset of f1 and it is a closed set. Eventually, basically this is an interval because this is f2 was intersection of two closed intervals, so this will be some interval here, f2, then we will have f3, and so on. And what will be limit n tending to infinity fn? So this will implies that limit n tending to infinity fn will be intersection of all sets. So basically we started with intersection I1, I2, so this is this f3 will be I1 intersection I2 intersection I3, and so on. So basically we are going towards intersection of all sets. So this is intersection n in n in. So now you can see that this sequence will converge to eventually a non-empty closed set. Which we are going somewhere like this, which is I. Clearly, again, using the fact that arbitrary intersection of closed sets is again closed, this implies I is closed and non-empty because each fi is non-empty, so eventually the final set will also be non-empty. Yes, closed and non-empty. So the main idea was to visualize how this intersection will look like. So is it clear?
Yes.
Okay. Okay, then let's move to next question. Question number 8. Which of the following statements is true? First one says that R minus Q is open but not close. R minus Q is open but not closed. Then we have R minus Q is closed but not open. Then we have R minus Q is both open and closed. And fourth, R minus Q is neither open nor closed. In order to understand this problem, one must be aware of the fact that the set of rationals is neither open nor closed. We'll see how. Yeah. Firstly, we make a remark that the set of rationals is neither open nor closed. Okay, let's see how. Firstly, let's start with open. Suppose Q is open, that means Q is equal to the set of all interior points of Q. That means each point of Q is, for every Q in Q, Q is an interior point of Q. That means there exists some R Q positive, obviously it will depend on the point Q, such that this interval Q minus RQ to Q plus RQ, this will be contained in Q. So what we are saying, that if this is the real line, this is a point Q, then this interval Q minus RQ to Q plus RQ must be contained completely in the set of rational numbers. But by density theorem, we all know that within an interval, I don't think there is any subset of R which is neither open nor closed. No, Q will be neither open nor closed. We can always find. How can you say that? Okay, we'll see how this set of rationals. In fact, this is a very good example. We should always remember the set of rationals and irrationals are neither open nor closed. Okay. Yeah. But by density theorem, we know that this interval will contain infinite number of irrationals as well. There will be infinite rationals as well as irrationals. But by density theorem, we know that this intersection Q minus RQ, Q plus RQ with the set of irrationals is non-empty. Therefore, the set cannot be contained in the set of rationals only. And hence, Q is not. Now, this gives us a contradiction. Therefore, by contradiction, Q is not an interior point of capital Q, which implies capital Q is not open. I hope until here it is clear that set of rationals is not open. Is it fine? That set of rationals is not open. Next, we will see that it is not even closed. Yeah, please let me know if this is fine. It is either an open topology, in which case it is open, its complement is closed. Take any point in R minus Q. So here I guess we are talking about the set of real numbers and the usual topology. If we consider the set of real numbers on the usual topology, Euclidean topology, on that the set of rationals cannot be closed or open. Okay. Okay, so till here is it fine? Please let me know if you have any doubt in any step I have done till now. Okay, next we'll see that this will not be closed as well. That can be done in a similar way. Uh, Next, one can see that I think you can try yourself. Since the set R minus Q is not open, try this. Try proving it yourself exactly the similar way we did above. Try proving it yourself exactly how we did above, because again you will be using the density theorem. Now since R minus Q is not open, therefore Q is not closed, because we know that a set is closed if and only if its complement is open. So therefore Q is neither open nor closed, which would eventually imply that R minus Q is neither closed nor open. So from here, our point 4 is true. This is the correct answer. R minus Q is neither open nor closed. I hope this solution is fine. If you have any doubt at any step in whatever I did, please ask. So, okay, it's okay that you're not able to understand. So, is there any issue in what I did? See, I want to show that the set of rationals is neither open nor closed. For that, firstly, I started to show that Q is not open. By contradiction, I started with suppose Q is open. ठीक है. If this is open, every point of rationals must be an interior point by the definition of open set. But what does the definition of interior point says? It says that there exists an interval, there exists a neighborhood around that point, which is completely contained in the set. This. Hmm? Now, since by density theorem, we can always find some irrationals in every interval. So there will be some irrationals in between in this interval. So this cannot lie completely in the set of rationals. Therefore, by contradiction, the set is not open. Now, similarly, using density theorem, you can show that the set of irrationals will not be open. Again, because when one will look for the interval, one will get infinite number of rationals in that interval. So eventually that would not be a subset of Q complement. So therefore R minus Q is not open, and we know that a set is closed if and only if its complement is open. Therefore Q is not closed. Hence, if the set is not open, then its complement is closed. How? I think you're not getting the definition. We are saying that a set A is closed if and only if R minus A is open. You're saying if the set is not open, then its complement is closed. No. If a set is not open, we cannot say anything about its complement. I don't think there is such a theorem. For example, I can contradict your statement. If we take A to B, close interval A to B, according to your statement, clearly this A is not an open set, then its complement should be closed, but its complement is minus infinity to A union B to infinity. This is open, not closed. We only have this result. If a set is closed, its complement is open. If a set is open, its complement is closed. Yeah, a set can be both open and closed as well. For that, we have just two examples, the set empty set and the set of whole set, the set of real numbers. A set can be both open and closed as well. Because see, if we consider the empty set, it is both. Since it is open, its complement is R, it's closed. Since it is closed, its complement R, it's open. Both the sets, empty set and the set of real numbers, is open as well as closed. So we have example of sets which are both open and closed. We have example of sets which are neither open nor closed. So is it fine now? All we know is that if a set is open, its complement is closed. If a set is closed, its complement is open. If a set is not open, I don't think we can say anything about its complement. So I hope this is fine. And yeah, this is a very good point to remember. One should remember that these basic examples, the set of rationals, irrationals, they are both open as well as they are neither open nor closed. And the empty set, the whole set are both open and closed. Next, we have question number 9. Let A and B be subset of R such that A is open and B is closed. Then we have some options which basically asks us to check whether A minus B is open or closed. We need to check that, to check whether A minus B and B minus A are open or closed. So basically we need to analyze these sets A minus B and B minus A. Now let's start with solution. Clearly A minus B is a subset of A, which is an open set. So we can try to think whether maybe this A minus B is open also. Not necessarily true, but we get some idea. Okay, so let's start with how to prove that a set is open. Now this will be open only if its set of interior points is itself. So let X be the set A minus B. And that means if X belongs to capital X, which is A minus B, this implies X belongs to A and X does not belong to B. Now this implies, now we will use the fact that A is open. Now since A is open, there exists some R positive such that X minus R to X plus R, this interval is completely contained in A. And since X is not contained in B, this implies this interval X minus R to X plus R can never be contained in B. Obviously, because X belongs to this interval, a point in this interval is not lying in B, so eventually this interval is not a subset of B. Now this tells us that X minus R to X plus R, this interval is contained in A minus B. We started with a point in A minus B, and we have shown that there exists some R positive such that this R neighborhood of this point X lies in the set X, capital X. That means this small x is an interior point of X. Now since X belonging to A minus B is arbitrary, we started with arbitrary point, that means every point in A minus B is an interior point of A minus B. Every point in A minus B is an interior point of A minus B. That means A minus B is an open set. So therefore, the options third and fourth gets discarded because they says that A minus B, no, A minus B need not be open. Okay, so let's not talk about the points. Okay, next let's look for the closeness. We'll show that the set B minus A will be close. Next we claim that B minus A is closed. Let's see how. A minus B is open. So basically, yeah, either point 1 or 2 is true. So for that, we need to see whether B minus A will be closed or not. Now, this implies either first or second is true. Either first or second is the correct option. So next, let's look for B minus A. Now let's start with some limit point of B minus A. Let y belongs to B minus A prime. That means y is a limit point of B minus A. That means y minus r, y plus r intersection B minus A minus singleton y. This is non-empty for every R positive. Now this implies mm, y minus R to y plus R intersection B minus singleton Y. This is non-empty as well, because B minus A is the subset of B, and since the intersection is non-empty for the smaller set, or eventually it will be non-empty for the larger set as well. Since if A is a subset of B and X intersection A is non-empty, that would imply that X intersection B is non-empty as well. Here B minus A, or instead B minus A minus Y is a subset of B minus Y, obviously. Now, since this is happening, by definition, Y turns out to be the limit point of B. This implies Y is a limit point of B. That means Y belongs to B prime. Now, since we are given that B is a closed set, this will be a subset of B, since B is closed. Therefore, Y belongs to B. Next, we will show that Y does not belong to A. Now, suppose if possible, Y belongs to A. Now, since A is an open set, so A is equal to A naught. That means Y is an interior point of A. That means there exists some R bar positive such that Y minus R bar to Y plus R bar, this is contained completely in A. That means Y minus R bar, Y plus R bar intersection with B minus A. Now, since this interval was completely in A and we are discarding the set A from B, so this intersection will be empty. But since we had proved above, let me mark this as, yeah, let me mark this one as equation 1. Okay, so from here, clearly since Y is an element of A, so discarding A will be same as discarding Y as well. So from here, we can write this as Y minus R bar, Y plus R bar, intersection B minus A, minus Y. This is empty. But by equation first, Y minus R, Y plus R, intersection B minus A, minus Y, this is non-empty for every R positive. That means this should be non-empty for R equals to R bar as well. Hence, we get a contradiction. A set is closed if and only if complement of the set is open. So the contrapositive of the statement is the complement of a set is not open implies the set is not closed. Yeah, you're saying that if A is closed implies a complement is open, and complement of a set is not open, a complement is not open implies A is not closed. Yeah, you're correct. Yeah, we say that P implies Q, not not Q will imply not P. Now this is correct. Is it fine now, Subrat? Are you able to understand what she explained? Okay, so from here, by contradiction, we get Y does not belong to A. So we started, therefore, Y belongs to B, Y does not belong to A. This implies Y belongs to B minus A. So we started with the fact that Y belongs to B minus A prime, and we got that Y belongs to B minus A, which implies that B minus A prime is a subset of B minus A, and hence B minus A is closed. So therefore, our option first is correct. A minus B is open and B minus A is closed. I hope this proof is fine. How we are able to show that A minus B will be open and B minus A will be closed. Okay, we are left with one last problem. Let's discuss that. I think
Read
this
the
is,
question once again.
yes. So are you asking about the options? Actually, I'm looking at the same assignment sheet, assignment of week 3. You can go through that.
Okay.
Okay. I think this is a good practice since the last date for week 3 was done, so I could discuss it. In next class, I'll discuss week 4. So in that way, even you'll be able to follow whatever I'm doing. Otherwise, I was doing something else and something else was going on in class. Okay, so now last problem, question number 10. Consider the following subsets of R. We have A, close interval 0 to 1, union 5 to 6. Then we have B, all those X in R such that X is greater than equal to 0. C, all those X in close interval 0 to 1 such that X belongs to R minus 2. So basically these are irrationals in the set close 0 to 1. And which of the following is true? We have first option, A, B and C are compact. Then we have A, B are compact, but C is not. Then we have A is compact, but B and C are not. And fourth, none of them is compact. None of A, B, and C are compact. So again, compact means closed and bounded. So can you tell me which of these three sets are closed and bounded? So if we look at first, is it closed? Or at least you can tell me whether it is bounded or not.
Yes, ma'am, it is bounded.
It is bounded, as well as this is union of just two closed sets. So this will be bounded and closed. And what about set B? Will it be bounded? So basically, this is the set of all points from 0 to infinity, na? All x greater than equal to 0. So this is unbounded above. Unbounded above. Unbounded above. Therefore, we cannot say this is compact. And what about this set C? So this is compact. B is not. The set C. Is it bounded?
Yes, ma'am.
Yes, because uh, all the points are between 0 and 1 for every x in C. So this implies C is bounded. But since C is a subset of set of rationals, we know that set of rationals are not closed. So basically, the set of limit points, when will look for the limit points of C, C prime will be closed interval 0 to 1, which is not contained in Q. Sorry, which is not contained in C. So basically, C, C is not closed. Whenever you have a subset of Q, that can never be a closed set. So therefore, B was unbounded but closed. Yeah, this is we can say one can easily check this is a closed set. This is closed but not bounded. The set C is bounded but not closed. So eventually B and C are not compact. So the only compact set is A. So our option third is correct. A is compact but B and C are not. I hope this is fine. And if you have any doubt in any problem we did today, please ask. Any
Ma'am,
problem
where
for
are you collecting these type of questions? Like, in which book are you referring these questions?
So today though I did assignment problems. Whatever
Okay, ma'am.
was your assignment 3, even I was having problem that where should I follow all these problems. So because maybe I was doing something from where I whatever I did in my graduation that was not coordinating with your course structure. So I got this idea since the last date for week 3 has gone, so now I can discuss. So in next class I'll discuss that for week 4. So that would be helpful for you also, because eventually you will have to look for the assignments now. So that would be kind of revision for you, and you'll also get to know that whatever what things you did wrong and how you were thinking but what should have been taught. So yeah, from now on, we'll discuss the assignment problems. And if you have any set of problems that you want me to discuss, whether something that was discussed in class but you were not able to understand, or anything of that sort, you can always ask me beforehand. You can also message me on this Teams even before the class if you want something specific to be discussed. Okay. So yeah, if you have
Yes,
any
ma'am.
doubt, okay then. Okay, if it's fine, we'll meet next Saturday. Thank you.
Okay, ma'am.